of the class on B, and then a couple trailers on C and D. So let's take a look at what the answer actually is in terms of the number of recruits. And so it's 22.8 recruits at the end of the year. Now here's where it's interesting in a sense. Is there such thing as 22.8 recruits? No. I've never seen 0.8 of a snake before. So this is where the math and reality has a tendency to break down. But for the mathematical construct, go ahead with using the decimal. Now typically when we come to an answer on an examination, I'll give you something like, if it was a percentile like this, first of all, it's going to be easy percentile calculus. But then it would be something like, when does the population size, when is it bigger than 22 snakes or something like that, right? Because you can't have 22.8 snakes. So it's like, when is it going to be bigger than 22? At what year does it cross 23 or something? So it'll be very clear. If it's not an integer value that you're solving, that you solve for, then it will be, is it greater than or is it less than, right? So in this case, there's some discrepancy there. Why? This is because there's lots of order of operations in the equation. That's it. So you got a lot of stuff to multiply, you got some stuff to subtract. And so what happens is it's easy to make a silly error. So if you got this wrong, go back and do it again at leisure. And make sure you get your order of operations right. Multiplication, division, subtraction, addition, and you do them in the proper order. It's just an ordering event. That's all it is. And that usually is what causes the discrepancy and the slight play in those answers. All right, so you have 22.8. So the next question is pretty darn easy, right? What's the total population size? Just plug it in real fast for me. They're very close to the tape, so go ahead and put that answer in. There we go. Very nice. Stop it right there. And in that case, we're looking at 98% consensus, so it's real tight. So again, we had 6. What do we add to it? 22.8. So in this case, what are we going to get? We're going to get B, which is basically 28.8 is the total population size of snakes. They did pretty damn good for having a bad capture efficiency, right? So in this case, you can see that the model predicts that the impacts of predators can be very, very severe on prey population. These predators were absolutely able to extinguish the overall population of this endangered species in this theoretical construct. So that's how it worked on as a model in theory. What about reality? Once we come up with the model, what do we have to do now? We know how to use it, so now we know what do we need to do? Test it. That's exactly it. Test it. So back to Gauss again, 1934, another classic experiment. He was the first experimentally tested lockable terror predator prey model as well. And so this is what he found. He manipulated protozoans in an oatmeal medium. And then he manipulated their predator, which is called diadinium. So when you look at it, this is paramecium. You guys were in high school. Did you ever look at paramecium under the microscopes? How many people did that? Raise your hands high. Yeah, most people should have done that. If you didn't do that, I'm a little surprised. All right? Because that's kind of the classic thing you do. It's one of the first organisms you look at. You throw them under the scope, you slow them down, you feed them, things like that. They're a common test organism. I'm actually working up a brand new ecology lab for not this year, but the next year, where we'll be using paramecium and doing this experiment, actually. Okay? So in this case, this is the predator, diadinium. This is the prey, paramecium. And this is how it attacks it. See that little kind of piercing piece on the end right there, that little nodule? They stab through the wall and they basically suck out the insides of the animal. It's pretty effective. And they're really voracious predators. So when he put these together, what did he expect to find? Based on the model. Oscillations through time with no change whatsoever as long as he didn't tweak initial conditions. But guess what? He didn't get that. This is what he got. So what happened was, the predator density, the prey came up just like expected, the predator density came up like expected, but the predators were so voracious they wiped out all the prey. They wiped them out so effectively there wasn't enough for them to eat, so what happened to them? They died too. So they exterminated their food, there was no other food supply around, and they went, both of them went extinct. Did the model predict that?
No.
The model doesn't predict that at all. It didn't work at all. Complete failure. Here's another one. This one was done in 1957 by Ukita. He took a look at these weevils here, which are really nasty pests of certain kinds of plant species that we like to consume, and then a parasitic wasp that preys on them. And so he manipulated this bean weevil, which was the host of the parasitic wasp. And so in this case, when he put them together, he watched for oscillations and he got them. But something else happened. It worked for a while, but notice what happened in the oscillations through time. They started out just like the model predicted, but then what happened to them? They got smaller and smaller, and all of a sudden they got what? They reached just like their carrying capacity, they reached what? An equilibrium, where they didn't change. They were stable through time. Did the model predict that? The model doesn't predict that. So for 112 cycles, it looked just like the model. But then all of a sudden, boom, it went down. 14 complete oscillations, and then it converged upon itself, not being model predictive at all. So again, quite different. Had he stopped at 13 oscillations, it would have looked like what?
The model.
Just like the model, but they went further and actually found that it was not a model match. All right. Well, why not? Before I go there. It didn't work. Why didn't it work? It was failure. Whenever a model does not match the reality, what does it mean about the model?
There's something missing.
What was breached?
One of the assumptions.
One of the assumptions of the model was breached, okay? Or it's missing something. All right, so what was the problem with the model? What do you think? Why did it not work? It was a lab experiment, so what? It's a good idea, but that's not it. What does the model assume? Exponential growth. What's the problem with that?
It's not realistic.
It's not realistic. Why? Because it assumes that the environment has what? Unlimited resources. If you pop basically a paramecium into a test tube, are there unlimited resources?
No.
There are not. There is a what in there? There is a carrying capacity in there. Does the model predict that? Does it even know there's such thing exists? It doesn't. So it fails. So how do we make the model better? We need to add the carrying capacity. How do I change this model to make it more relative and more relevant to the vast majority of populations on the planet? I don't use Rn, I use what? Rn times K minus N over K. So if I add the logistic growth model as the growth kernel and then rerun it, this is what it will predict. So if I basically do exactly the same thing, but instead of Rn, I add the K minus N over K to it, this is what I'm going to find. Now this is what it predicts. That's interesting. It predicts oscillations to convergence and equilibrium. Is that a model match now to the Ukita experiment? It's a perfect match. It also predicts this, that very first thing that the original model predicted was stable oscillations. We haven't seen those yet. But then it also predicts this, extinction. Now is it a model match? It is. So notice how the predator in the model predictions goes up, but if there's nothing to eat, it will too do what? It will die. In reality, that doesn't occur typically very much. Do you know why?
Different prey.
Because predators are not stupid. They will do what?
Eat other things.
They will switch to other things. It says it'd be like you walking to your refrigerator saying, you have a full refrigerator full of food, and you're like, there's no pizza. I'm just going to starve to death. Would you really do that? No, you'd eat something else, and that's what predators do. They're not fools. So they'll exterminate the prey to low levels and then switch to something else. So again, this is a theoretical construct, right? But look what it's doing. It's predicting accurately now the outcome of those experiments, whereas the first model did not. Because the first experiments had what implicit in them? A carrying capacity. Well, this model talks about carrying capacity, so it's a fine match. Why? The assumptions of the first model were breached. That's why it didn't work. In this case, the assumptions hold true for the experiments. You get predictive outcomes that are good matches, and it works well. All right. Now, I just showed you this model to show you that how that works better. In terms of computational solutions, I'm only going to use the simple exponential model, okay? I mean, that's the one I'll use for computations. But I want to show you this one because it's much more reality-based and does a better job. But it gets thick to solve with the time limits that we have, and that's why I'm not having you do a computation, okay? All right. So, model predicts that you can slam the prey, and you can do a good job of it if you're a predator. Does that hold? Well, when we look around the world, we see, yeah, it holds. Predators can really do a number on their prey populations in terms of regulating them or driving them to extinction. Here's a nice example of it. So, this fish over here is the sea lamprey, okay? The ones that are hanging off the bigger fish, which is a lake trout. I want to turn the lights down a little bit just so you guys can get a good view of this, okay? So, lake trout are native to one of the largest inland water bodies in the world, which are the Great Lakes that we have in North America, right? So, the area around the Great Lakes used to be a site of massive industrial strength for the United States. We used to produce all kinds of products there. All kinds of steel mills and all kinds of great things were shipped out and sent all over the world. But that industry collapsed over time. It was outcompeted. Sites shifted to different places in the country, different places in the world, and it kind of collapsed as an industrial center. Now it's referred to as like the Rust Belt and things like that. There's lots of people who are disgruntled, they don't have jobs. It's not the nicest place in some cases. Other areas are still real nice, but it's not the industrial powerhouse it used to be. So back when it was a strong and vibrant community in terms of industrial power, the issue was, how do we get the stuff we built there to the coast so we can ship it around the world? Because you had to send it over rail line, and that took time and it was expensive. Because you had to get it onto boats and then move it. So the idea was, can we have a way to bring the boats to us? So the idea was, let's carve a pathway from the lakes to the ocean. Because it's close enough that it's worth the investment, and that's exactly what they did. So they built this thing called the Welland Canal. And basically, it was a highway from the lakes to the ocean, and the boats would just go back and forth, and it increased the speed of commerce, and everybody did real well and made a lot of money. The problem with that, however, is you've just opened up two habitats that have never been in contact with each other. So you've basically established a freeway between the ocean and the freshwater system. And one of the first organisms to take advantage of that freeway was this ectoparasitic fish, the lamprey. So this thing attaches on to other fish. It has chitinous teeth. Here's an example of the teeth and the wound that it leaves. It burrows into the side of the flesh of the fish, penetrates it, and then sucks out all the fluids, okay? Blood, lymphatic fluid. And the fish typically do not die from the bite, but when the lamprey detaches, they leave these open wounds. So water is filled with bacteria and fungus, which then invade the fish and then kill the fish via infection. So if you ever get cuts and stuff, you probably should not actually wash them in rivers, because they're actually quite dirty. And I work in rivers, I'm a river ecologist. I had a friend of mine broke her nose in the river, made the mistake, because they were freaked out, because the blood was pouring out, of getting the water and splashing it on them, ended up getting a massive infection in the nose and had to have all kinds of surgeries to get rid of it, right? Not a pleasant experience. So even though it looks clean, often it was not. So that's what invades the fish and kills them. So this is what happened. They built the canal. Well, in 1829, that canal was built. By 1921, they discovered the first lamprey. And it quickly spread. So it started in Lake Erie. That was in 21. And then in 36, it went to Michigan. And then in 37, it was Huron. And then in basically 45, it was Superior. And it spread throughout the entire lakes like an invasive wave. You can kind of see red spreading distribution. Within 20 years of introduction, it had completely decimated fisheries within the lakes. Think how big the Great Lakes are. They're massive. They're larger than many kind of bounded seas, right? They're massive bodies of water. Up until this time, before the building of the Welland Canal, there were massive commercial fisheries of freshwater fishes. So lake trout can get 30, 40 pounds. And so they're really good eating too. So you would catch them, ship them out as a food source. And there were literally communities of fishermen and a whole industry in the lakes built around their capture. Well, what happened was the lamprey was such an effective parasite predator / do the same thing, right? That they decimated the stock of lake trout to almost nothing. So it collapsed the entire lake trout fishery and all those people lost their jobs. At that point, it wasn't like the model, because the lamprey didn't just say, oh, no lake trout, I'll just die. What did they do? They switched, and they switched to the next largest fish, which was this whitefish in the lake, and they decimated that. So they basically collapsed every commercial fishery in the lake and collapsed the entire commercial fishery fleet all across the Great Lakes, and thousands of people lost their jobs and livelihood. All right, pretty bad news. So they tried to figure out how to get rid of the damn thing. They tried all kinds of stuff. Invasive species are not easy to get rid of once they become established. They tried all kinds of pesticides on it to basically remove the thing. Nothing worked. They tried all kinds of stuff. There was nothing that would really consume it. So they got an interesting idea. This thing at certain times of the year travels up to small rivers from the lakes to breed. Like salmon, you know how they travel upstream? This thing does the same thing. However, this is a cartilaginous fish. It's not a bony fish like the trout it's feeding on, which means it's not a very strong swimmer. But it does get upstream. It takes it a while. So what they discovered is as it made its way upstream, if it hit any kind of obstacles in the river, like let's say a little waterfall like this from here to there, it was unable to get over the top of the waterfall. And they would accumulate by the thousands behind the obstacle because they couldn't make their way upstream. The trout, on the other hand, zoop, right over it, no problem at all, because they're strong, right? They have that big bony structural support system for their muscles, and they're able to clear those obstacles like they're nothing. But for the lamprey, So someone had a really ingenious idea. They started by just going below wherever there were natural boundaries like that, and they would just get big nets and grab them in the nets and throw them on the shore and kill them. But that required a lot of human labor hours to do. So someone got a really great idea. And often, you ever heard of the KISS rule? The KISS rule is something that I give to my graduate students when they walk in the door on day one, right? Because when graduate students come in, they have all these grandiose ideas. I'm going to build the best of this and the greatest of that. And that's really awesome, and I'm happy for you, but it'll almost always fail. And our grad students have to learn. I did the same thing. My first experiment was this giant, elaborate, beautiful thing. I thought I was going to be the best thing in the world. Ended up being a complete disaster. Fell apart, all noisy and messy. And then you learn the simpler it is, the cleaner your information becomes. So this is really like that. They tried all this complicated stuff to get rid of it. Nothing worked. Someone looked at that and said, I got a plan. And what they did was they went out to it. And what they would do is they started with natural boundaries, right, these natural kind of places, and they get plates of steel. You're in the Rust Belt, right? Steel is everywhere. So they grab plates of steel, they'd slap them down below the little waterfall, and then they'd go up to it and hook up car batteries to it, and just go clear, and it'd kill them by the thousands. It was so effective that what they did was they built artificial dams about 2 feet high. Any barrier to the fish, the lake trout, the natural rainbow trout, all the trout, the brook trout stuff that are in there? No problem. Go right over them, nothing. But for lamprey, since they're cartilaginous, they're not good swimmers, they can't jump. So they would pile up behind these things, built below it were steel plates, and they got a guy with a truck who drives around every spring. He comes up to the spot, he hooks up the batteries to the plate, he charges it, kills the lampreys, goes to the next spot down the river. It was so effective that it decimated lamprey populations all across the lakes. And those are big lakes, right? Got to the point now where we actually have not a commercial fishery, but we do have a sport fishery back of all the fish that the lamprey decimated. Unfortunately, some of them are not the best to eat because the Great Lakes are highly polluted because of all the industry that was around the Great Lakes. But it's definitely coming back in terms of the fish populations. So the take home on this is, damn, predators can really make an impact, and at large scales too. All right. Now, I've shown you examples of all those predictions from the Lotka-Volterra predator-prey model assuming logistic growth, except for one we haven't seen yet. Which one was it? The very first one that was predicted, which was these neutrally stable oscillations through time. That was not so easy to find in nature. We have a couple of approximations from it, but even they're not the best fit. Now this is probably the closest thing we have. So this is an example with the snowshoe hare and the lynx. So there's the snowshoe hare trying to escape, he's kind of blending in the background, and the lynx is about to cuff out and grab it. Lynx are basically wild cats, they're very smart. They're thoroughly aggressive and they're real voracious predators. And so in this particular case, you can actually look at these oscillations going all the way back to the 1800s when they first started taking records of like furs and things like that from trapping, all the way through, and this is just a short window, but it goes all the way to today. And it's a little rough, but can you see the oscillations there? They're pretty easy to see. They go up and they go down. First their hair comes up, followed by the lynx, and then they go up and down, up and down. And it's real consistent. This cycle actually occurs continuously across the entire North American continent from the west coast all the way to the east coast, almost in synchrony. It's a really interesting feature. They call it a 10-year cycle, but in reality it varies between 8 and 11 years in terms of its duration. Now, how does it basically work? Well, what happens in this thing is you have hares, and they decline due to decreases in their birth rate, their growth rates, and increased mortality due to consumption by the lynx. Well, it actually has to do with the way that hares multiply. What kind of society do rabbits have? How does it look like? You know? How's it structured? Are rabbits solitary? Rabbits are typically not solitary. They are communal. And they operate a lot like prairie dog towns. Right? They have these things called warrens where you have a bunch of rabbits together. Well, the thing about the warren is a safe place if you're a rabbit because you're underground, hardly anything can get at you unless you're a weasel or something like that, right? So it's a real safe place to be. So what happens is as they start to feed, they try to feed close to the warren because it's safer. You can dart back to safety. But as their numbers grow, what are they forced to do?
Spread out.
Spread out further and further away from the warren to grab browse, right, food, and that makes them more susceptible to predation. So the more they are, the more they decimate their local crop, and they have to range further. Now the lynx is very smart. As soon as it starts to see that there are hare around, and it likes to eat hare, it will begin to specialize on them, right? And it will start to hunt them exclusively. And they learn very quickly how to hunt them and do a very good job of hunting them, right? And they start to have really big impacts on their numbers and drive them down. So as predation increases, what you're going to see, the lynx population density will go up, and the hare population density will go down, and it will drive this curve. Well, that seems like a pretty good match to the model, right? However, it's more complicated than that. Because what the model basically says that the prey drive the predator, and that's how it works. But something's actually driving the prey population. So in order to start this thing, you have to have an expansion of the prey population. And what causes it is resources, right? So if I have good resources in a given year due to rainfall, what will that generate the production of?
Plants.
Plants. The more plants, the more what?
Rabbits.
The more rabbits, the more rabbits, the more
Lynx.
lynx. That's exactly how it works. So superimposed on this is actually a third oscillation, which is the plant oscillation driven entirely by wet years. And so the entire oscillation cycle, this 8 to 11 year cycle, matches perfectly with the years that are really wet. And that's what starts the initial cycle and projects it forward in time. Without the plant cycle, there's no hare cycle. Without a hare cycle, there is no lynx cycle. So it's actually 3 superimposed on each other. The model, does it predict 3 things? It does a good job of predicting plant and hare, and it does a good job of predicting hare and lynx, but it doesn't predict all 3 at the same time. And so again, that's kind of an anomaly where the math breaks down with the reality. All right. So again, 2 cycles are generated by the interaction between the first, which is actually the hare and the plant cycle, which influences the hare and the lynx cycle. All right. Well, if predators are so damn good at what they do, how do prey manage to hang on, right? Because we've shown examples where they've decimated the prey. Well, prey are not as susceptible as you may think. And so there's a variety of reasons why. The first is lots of prey have spatial or temporal refuge. If you want to eat me during the day, I'll just do what? I'll come out at night. If you want to eat me on the top of the ground, I'll just do what? I'll go underground. So there's that would be spatial refuges or temporal refuges. Okay, so there's different ways. You avoid the time in which your predator is active. Remember the black rat and the mongoose? It's a classic example of the temporal separation that saves the rat from consumption. Optimal foraging is also a very, very common thing. We've already been talking about that. When the prey numbers become too low of its preferred food source, what will the predator do? They'll just switch on to the next most abundant thing and eat that. And when that number gets too low, they'll switch to something else. By the time they come back to the original prey population, it's already rebounded because it hasn't been preyed upon by X amount of time. So what this does is by the predator hopping from prey to prey to prey, which is most abundant, it allows all the prey to survive in that particular habitat with none being driven to extinction. So that would be an example of optimal foraging. There's all kinds of adaptive traits that organisms have to avoid being preyed upon. We're going to talk about this in gory detail when we deal with evolution. But there are three things that are adaptive. The way you look, morphology, the way you function, physiology, and the way you act, which is behavior. Those are things that become adaptive over time, change in the genetic structure. So all these anti-predator strategies are versions of that. The first would be an example like chemical defense. So this frog over here is a poison dart frog. I don't know, lights them up, they're real colorful and cool. That's a really dangerous organism. So frogs in general are not the toughest creatures in the world. They got soft skin. They don't really have much of anything in terms of claws or teeth. The closest thing they have to teeth are these little stubby nodules. It's like if your finger's in a toad's mouth, it's like, yeah, whatever. It's nothing. And they don't have strong jaw apparatus or anything like that. They look pretty weak, but they're actually pretty formidable because they have toxic defenses in the form of mucus that can be highly caustic and highly toxic. Here's a nice example with this dart frog. Well, I call it dart frog because natives rub the backs of their barbs on it, they shoot it, and what it will do is it actually stop the contraction of muscles, including your diaphragm. No diaphragm contraction, no breathing, you suffocate and die. If you were to actually touch this frog, like this guy has it right here, and you had a cut on your hand, you could be in for deep trouble. You could kill yourself. So it's really important to kind of know what you're doing when handling something like this. So chemical defenses are quite common. Anybody from the Bay Area? In the Bay, there's a big toad. You guys ever seen it? It's called Bufo marinus. You seen that thing? So it's this big, kind of ugly toad. When toads are threatened, what they do is a couple of things. They do some behavioral things where they kind of blow up and they make themselves look bigger. But they secrete toxic mucus a lot of the times, too. Bufo marinus is an example of this. And so the toxin is strong enough to, like, if a dog were to eat it, it would kill the dog. Pretty powerful. If you were to eat it, it'd make you sick as a dog, it could kill you. But that mucus is really toxic too. Someone in the Bay Area for a while, you ever heard this thing called toad licking? That was actually a true thing that happened. Someone got the bright idea that the back of that slime that they produce, it actually has a mild hallucinogenic property to it because it's toxicant, kind of like the eucalyptus was, right? And so someone got the bright idea that if you lick the back of them, we'll get a hallucinogenic high. And I'm kind of thinking, if you're willing to lick the back of a toad slime, you don't need anything else. It's there. You're done. Stop. Right? You don't need anything. Yeah, pretty gross, but pretty effective. Okay. Camouflage is another. So basically, the ability to blend in, that gives no information whatsoever. And so you're avoiding capture. Think about the model. What do you instantly decrease? C goes way down if they can't see you, and therefore your impact's going to be a lot less if you're preying on that particular species. Mimicry is another cool one. So if you see this over here, the second one from the left, that looks like a what to you? It looks like a bee or a what?
Wasp.
A wasp. Would you touch it?
No.
You've learned over time that if you see black and white stripes on something that flies, you should not touch it. And you learned that lesson pretty early on, either by getting stung by something that looks like that, or your mom or dad said, don't touch anything that's black or yellow like that, you'll get stung. And they freaked you out and you learned that lesson, right? How many people have been stung before? There you go. Lots of you have learned. How many people have not been stung? We should take you outside and have you get stung, just so you can experience it for yourself. It's an unpleasant experience. This, however, is neither a wasp nor a bee. It is a fly. It cannot sting you. It can do nothing to you. But would you touch it? Nope, because you think it can. And so this is another way to avoid being preyed upon because it's fooling the predator to think that it's nothing that would be palatable. Displays of intimidation and fighting. This is a real lizard. They're really cool. They're in Australia, they get about this big. When threatened, they like one of these horror movies like the Jurassic Park. They flare the thing, they stand up real tall, they hiss, and they'll flare this big frill at you, and they shake it, and they look real intimidating. We're tired. We're classic. So anyway, they're real intimidating. However, if you were to challenge that, what will they do? They're like, eek, and they run away. They're complete cowards, all right? But they give you this big show like they're all tough. They're not. But that can be very effective, and it can be quite startling if you're a predator and they respond like that. Agility is another one. Can you catch an impala in the Serengeti by yourself with no tech?
No.
Good luck, right? No, not going to happen. So agility, the ability to run fast and jump high are ways to get away. Armor is a great one. When you look at a turtle or a tortoise, that basic body plan has not changed for millions of years. Why?
It works.
If it ain't broke, don't fix it. I can say it any better. That's exactly right. It still works. And it works fabulously. So that's a great way. You just tuck in, predator rolls you over, bites on the outside, they can't get at you. Eventually they get bored and they walk away, and so do you. So it comes with some cost because it weighs you down and makes you slow, but it's a very effective way to avoid predation. The other one is to alter reproductive patterns. So this is referred to as masking. You see all the acorns on the ground? There's thousands of them. So many plants basically reproduce all at one time. And they'll flower, and then they'll shed seed all at once and produce millions and millions of seeds. Well, that's a giant sign that says, please come eat if you're a predator. However, can the predator eat them all? Too many. They get filled up, and the rest escape. They get through the bottleneck, right? So again, that's the way to do it. I gave you an animal that does exactly the same thing. What was it? The flamingo does exactly the same thing. They display masking, but in an animal sense, right? Predator swamp. So these are all reasons why prey exists, even in the face of intense predation. They have refuges, they screw with the predator's hunting behaviors by modifying their own behaviors, and they have a whole suite of morphological, physiological, and behavioral ways to reduce the consumptive and negative impacts of predation. All right, so we're going to sum this one up. In the same way I gave you a flow sheet for how an ecologist looks at distribution, I can also give you a flow sheet for how an ecologist looks at abundance, the numbers of things. So, the first thing we're interested in is in the density, right? Well, what is the density impacted by? There's a little weirdness in that. It should say changes in population numbers all in the same line. Does it say it on your, is it skewed on your notes?
Yeah.
Okay, that should just be on one line. It should say density at the top. So let me fix it real quick. All right, so we have density. We're interested in the changes in density over time, population dynamics, right? Well, what impacts that? Birth, death, and immigration, dispersal, right? Migration. Well, what impacts birth, death, and dispersal? Well, there are factors extrinsic to the organisms and factors that are intrinsic to the organisms. What are they? So intrinsic factors are the physiological and the behavioral components of an organism. Extrinsic factors are abiotically, what does the environment look like? Chemically and physically. Biotic, all the interactions of predation, herbivory, and competition. Symbiosis, which we talked about as well. And then resources that are available, nutrient space, etc. So factors external to the population and factors internal to the population. Again, it's screwed up. It should say physical, chemical there, okay? Will both impact natality, mortality, dispersal. Those will therefore impact density. And that's how we would address looking at abundance of populations and how they change either high, low, or stay the same over time. That's abundance. All right. The next thing we're going to take a look at are communities.
Super bad. horrible. You stopped me from procrastinating. I'll show you after class what I was doing for past 12. It's on my snaps though.
So we've worked our way through population ecology, and now we're going to touch base on community ecology. Now, just to give you a little sliver of ecosystem ecology too. So remember, what's a community? Two or more populations in
Same geographic.
the same place, the same geographic location. All right. So communities have different characteristics. They have trophic structure. Well, what does that mean? If I was to take a look at the primary energy source that you start with, how many layers can you build on that of different organisms? So it would be plants, and then animals that eat plants, and then animals that eat animals, etc. So there are layers of energy flow. That would be the trophic level. I can talk about species diversity. How many species are there, and what is their relative abundance, their percentile in any community? That's another characteristic. I can look at dominance. What organism dominates a particular community? Coral reef is dominated by corals, yes? A tropical rainforest might be dominated by a particular type of tree depending on where you're at. So you can get dominance of certain organisms in the community. And then growth, form, and structure. We just talked about coral. What does it look like three-dimensionally, right? A rainforest has this three-dimensional partitioning of its basic framework, mostly in a vertical profile. So does the coral reef underwater. It shows different forms. So these are all different ways that we can categorize the characteristics of a particular community. So there are hypotheses to explain why you have this particular assemblage of species in one place and maybe not another. And so the first is this idea of the individualistic hypothesis by Gleason. And in this particular case, what it basically says is that communities are just chance assemblages of things, right? You happen to be there because you can deal with the abiotic conditions.